Hi, good afternoon. This is the presentation on the Connected Autonomous Vehicle Architecture Standard. It is a standard that has been developed by MPAI because we understand that connected autonomous vehicle will bring many benefits. The fact that the machine error rate can be lower than the human error rate because machine tend not to get tired. It doesn't mean that they don't, they are error free, but certainly we can design the machine to have a much lower error rate. Humans can have more time for activity they consider important. The vehicles and the infrastructure supporting them can be used more efficiently. The management of traffic can be handled better, and congestion and pollution can be reduced. Then we can say that elderly and disabled people can have a better life. So there are a lot of good reasons, but you know, one important element to make this idea possible is to have standards, because if we have standard, then we can reduce the cost of connected autonomous vehicles. So the purpose of MPAI and the PAI is the body that develops a standard on data coding based on artificial intelligence, is to specify standards for connected autonomous vehicles in steps. The first step is to specify a reference model that is broken down into subsystems. So we have the functions of each subsystem and the data exchange between subsystems, which means data between subsystem and subsystem, but also between human and subsystem, because the human needs to talk with a connected autonomous vehicle. Step two is to break down the subsystems in components. And for each component, we specify the functions of the component, the data exchange between the component, and the topology of connections of components. Finally, step three, for each component, we specify the functional requirement of the data exchange and the technology that are implied. They are an implementation of the functional requirements. So, if we have a connected autonomous vehicle reference model, we can iterate on that. And as a result, the research can concentrate, for instance, on a single component, where, say, the researcher or the group of researchers is particularly expert, and then they can optimize the operation, keeping the interfaces functional requirements. Industry can promote the definition of data formats when the results are mature and a component is needed, and users can, and this is very important, explain to some extent how the machine, the vehicle works. So what are the benefits of such a MPAI cloud standard? Is to accelerate the creation of a high-tech market, and I'm referring this as a model, what happened in the MPAI group in the domain of media, digital media standards, because a standard can foster higher quality vehicles, lower the prices of vehicles, enable explanation of how the system works, assuage consumer concern, and provide tools for regulation by including conformance testing and performance assessment in addition to the actual specification. Specification tells you how you make things, but you don't necessarily have the means to understand whether what you have done is correct or not. So what are the benefit of reference model to the market? Component manufacturers can develop optimized solutions based on specifications that are universally available. Then they can put their standard AI modules, the components, to a marketplace. So this for the component manufacturer, but car manufacturers, and of course there's an overlap between the two, but let me have this separation between the two, that car manufacturer can access a global component market that is based on standard functioning interfaces and can be tested for components using standard procedures. Regulators can communicate with market development and provide guidance. So this is an attempt at describing the few slides before. So we have standardization that underpins a research, component manufacturer, vehicle manufacturers, and service providers, and regulation that underpins vehicle manufacturers, service providers, and end users. So let me try and describe what is the scope of this connected autonomous vehicle architecture standard. So I said that this is a technical specification that specifies the architecture of a connected autonomous vehicle based on a reference model, and the reference model comprises a vehicle broken down into subsystems, for each of which functions, input, output data, and topology of components are specified. Each subsystem broken down into components of which functions and input, output data are specified. So the difference between a subsystem and a component is that in the first case, we have to specify how components are interconnected, and that is the topologies. Each subsystem is implemented as an AI workflow, and components are implemented as AI modules. They are executed in an AI framework that has been specified by the technical specification AI framework. So let's define what a CAV is. We define a CAV as a system that interacts with a human and understands the utterances, setting the missions. For instance, take me to lunch. Then, of course, I say interact. It is not just to receive, but it can engage in a conversation. Then plans the route from here to there, senses and represents the external environment, and by that I mean the space that is around the car, like us. So we sense and represent internally in our brain the external environment. Exchanges environment representation with other connected autonomous vehicles, decides how to execute the steps of the route, implement decision by issuing commands to actuate the decision that are made to move the vehicle to a certain point. So this is the reference model. It is here you have a human. Let's say that the human wants to get on board on the CAV and go somewhere, and so it says so to the subsystem that is called human CAV interaction. Then the human CAV interaction tells the autonomous motion subsystem that it should plan a route taken from here to there. So now the autonomous motion subsystem needs to understand where it is, and therefore it requires the environment sensing subsystem to provide the necessary information from the outside world. And of course, the environment sensing subsystem has many ways to understand where it is. So here is an example of sensor. Then not only sensors that are inside the environment sensing subsystem, but also other more mechanical system that provide the desired information. So after that, the environment sensing subsystem can respond to the autonomous motion subsystem by providing a first level of understanding of what the environment is. And based on that, the autonomous motion subsystem may respond and so on. Now, when the autonomous motion subsystem is moving, when the connected autonomous vehicle is moving, it can refine its representation of the environment by interacting with other connected autonomous vehicle or CAV-aware entities like roadside units and so on. So finally, the autonomous motion subsystem has sufficient information to tell the motion actuation subsystem, now I want to go from this place to that place. And this is implemented. I have a disclaimer in the sense that at the moment, we do not include the mechanical parts of a CAV. The standard does not include anything about that, only the interfaces of the motion actuation subsystem interacting with the mechanical part. That is what this interfaces will specify. We will use a number of terms and definitions. Some we have already seen: a human-car interaction, environment sensing subsystem, autonomous motion subsystem, motion actuation subsystem, environment sensing technology. Basic environment representation is what is sent from the environment sensing subsystem to the autonomous motion subsystem. Full environment representation is the representation that is acquired by the motion actuation subsystem by exchanging information with other vehicles around. So let's see more precisely the elements of the MPI-CAV architecture that are part of the specification. For each subsystem, we specify the functions, the reference architecture, the input and output data, and the topology of the components. For each component, we specify the functions, the reference architecture, the input and output data. Now, this is a reference model, but it doesn't mean that an implementer should necessarily implement all the components that are defined in the specification. The specification defines components at the atomic level, but an implementer can decide to merge some components, provided the external interfaces of the merged components are preserved. So this is the table of content of the standard. So this presentation will be made available at the on our website, the MPI website, mpi.community. And so everything that is here is a link. So for instance, you have we can have let me say the definitions. So we have a large number of definitions here. So here they are. So you see we have a large number of definitions, and you are welcome to navigate these definitions. Then we have the reference model. The reference model is here. It's nothing new because it is exactly what I have shown so far. But the difference is that here we have the input and output data of the connected autonomous vehicle. And so let me go back here to another component, which is the human-car interaction. So this is the first subsystem. So this is specified in 5 parts: the functions of the interaction. So this gives more in detail what happens between a human and the human-car interaction. This is the reference architecture. Well, the reference architecture is quite complicated. So here you have the audiovisual front end, and the audiovisual front end acts in two ways: by acquiring data from the outside, and for that, and in that case, it uses the environment sensing subsystem, or it can acquire data from the inside. And then here we have a large number of components which are specified by their function and by their input data. Well, this one, autonomous automatic speech recognition, is, well, that's clear what it does. The audiovisual alignment, this is important because it is something that is capable of getting the information about what is the audio scene and what is the visual scene, and align the audio object with the visual object. And the result are just the audiovisual object, because that's what we are interested in. Then we have natural language understanding, which is a basic component for human to machine interaction. We have another important component, which is the personal status extraction. So personal status is a simple example I make. I use emotion. Emotion is an example of personal status extraction, but we have more. We have a cognitive state, which is, okay, at this point in time, what is the level of my knowledge? So I can be absolutely ignorant, or I can know a few things. And so this must be described by this personal status extraction. And then we have a third component that is called social attitude, and that describes how the machine or the human, because here it is the human, places themselves vis-a-vis the environment. And finally, we have the entity dialogue processing, and this is the part that uses all the information, which is quite a significant amount of information, and uses that to decide what should be the answer in terms of text, but not only in terms of text, also in terms of the machine personal state, because the machine can have a personal state. Of course, it is not generated spontaneously like we human can. This is an artificial personal state, but it's useful to provide the appropriate response, not just in text, but also in attitude and emotion and so on. So then here we have the input-output data of the human-car interaction, and we have the functions of the AI modules. So here it says, let me go, for instance, here. Dialogue processing provide the machine text containing the response of the human-car interaction and the personal status of the machine. And finally, here are the input-output data, and you see them listed here. So I went into some details. Here I will try and be more quicker. So we have this is the architecture of the environment sensing subsystem. Here too we have the functions detailed. We have the reference model. So you see essentially we have something that computes the spatial attitude. Spatial attitude is position, orientation, their velocities and accelerations. That's what it is. So it is a data type that is specified by MPAI, and here we are simply reusing that. And here we have a number of AI modules that compute the scene description of what has been produced by radar, by LiDAR, by camera, ultrasound, audio, and then there are others. For instance, we have the traffic signal. So the scene description of the traffic signal. And here we have the same elements. Then we have the autonomous motion subsystem. And here too we have the functions, the reference architecture. So here we have the environment representation fusion. This receives the basic environment representation, exchanges data with other environment sensing subsystems, I mean external, and and then the remote autonomous motion subsystem and improves its representation of the environment. And then we have here too the input-output data and the functions of the AI modules and the input-output data of the autonomous motion subsystem. Finally, we have the motion actuation subsystem, and this provides, again, the functions, the reference architecture, the input-output data, the function, and the input-output data of the AI modules. So let me say a few words about what we have here. So here we have the autonomous motion subsystem that is the brain. And the brain is telling the legs to move the vehicle to a certain place. That of course so it issues a command, and this command is received here by the command interpreter. And the command interpreters have the task to receive, say, accelerate at 50 kilometers per hour and go to that particular place 50 meters away. But when you are there, you should turn right, and therefore you should reduce the velocity. So this converts into commands to the motor of the wheels, commands to the steering wheels, and to the brakes. And similarly, there will be a response, because the command can be implemented successfully. In that case, no problem. But there can be difficulties, and therefore some information is sent back that will be processed by that, and possibly sent back to other parts of the connected autonomous vehicle. We have the Cow to everything. This is not a normative. It is an initial specification of the communication, the radio communication of a connected autonomous vehicles with what is around in the space. Okay, so here we have with more details the functions of the human-car interactions. We have the functions of the environment sensor subsystem, the function of the motion autonomous subsystem, and the function of the motion actuation subsystem. There's one important point that we have added to this technical specification. I believe it is important because it is something that provides a new way of creating a model of how a connected autonomous vehicle can interact with other connected autonomous vehicles. So let me make a digression, because now I'm talking about the metaverse, and you may ask, why do we talk about the metaverse? Well, let me first lead you through this slide. So in MPAI, we have developed another technical specification, which you can find on the web, and you can attend the presentation this Friday at 1500 UTC. So it is an information and communication technology platform that is composed of processes, and the processes perform these functions, not necessarily all, but in general, all. To sense the data from the environment, process the sense data, produce environments that are populated by objects, process the objects in this metaverse instance or in other metaverse instances, and have an influence on the real world or the virtual world of the metaverse in ways that are consistent with the goals set for this metaverse, affect these actions within the capabilities of the metaverse instance, and this should be done while complying with the rules that are set from the M instance. So rules, for instance, means that you cannot accelerate in 2 seconds from 50 kilometers per hour to 100 kilometers per hour. That is an example of what is meant, or that you should obey traffic rules. So this is the MPI-MMM, so the metaverse model that we have. So it's a very simple part of what the specifications say. So we have the processes can be users, devices, apps, and services. And these processes perform actions on items. What is an item? Well, it is data and metadata that are recognized by the metaverse, and therefore can be acted on. So the user process represents a human's agency. So here you see the human, okay, here you have a device, and the human can use the device, and then we have this user. This user is a process. Is a process in the metaverse. It can run on the device as well, but the user is a process that represents the human, and the user is not the persona, it's not the avatar representing the human. That's another thing. It is the process that can be rendered as a persona and can act on communicate with other processes. A human can be presented by any user, and the user can only represent one human. These are two general comments. So this is what we have done, and unfortunately, it is a little bit complicated, so it would take too much time. But here it says essentially that we have a human here. The human interact with the human car interaction subsystem of their car. And so here we have all the interaction with the autonomous motion subsystem. Then here we have another car that is moving around, and there can be an exchange of information between these entities, so that the car A can improve its understanding of the environment. So, and all this can be specified in terms of primitives that are specified by the MPI metaverse model architecture specification. This is an important part. So we are saying here that the environment representation that the CAP creates can be expressed as a metaverse instance, and that the metaverse instance can be expressed using the primitive that have been standardized by the MPI metaverse model architecture standard. So here you have more in detail all the steps that make this possible, and so you will have the possibility to look in depth at what it is here. Okay, so this is what MPI has done so far. And you may ask, okay, is that the end of the world? No, certainly not. So because at the moment we have just provided the architecture, we have identified the subsystems, we have identified the components, we have identified the data that are exchanged between components, but we're not saying anything what these data are. So the first thing to do is to develop the functional requirements of the connected autonomous vehicle. So this is something that we are actually doing. And so as a result of this first analysis, we understand that many of the technologies that MPAI is standardized in different contexts. We have, at the moment, we have 11 standards, and we have picked the necessary technology for each of them, and we can see that most of them can be used, can be adapted to the CAP context. It doesn't mean that we have all the technologies, and even if we had our rules imposed on us to develop a call for technologies where we say, hey, this is what we have. These are the requirements. These are the technologies that we already have. Do you think that these are adequate? Or do you have better technologies that can do the job? So if you have them, then please submit them. But we have an important point. We have the notion of framework license that we always have for all our standards, and this is still to be developed. So we plan on publishing this MPI-CAV data call for technologies in a couple of months. And this is the plan. And so just to show you concretely that what I'm saying is true. Here you have the tables that you can find in the specification on the web. You see some red things here. What do they mean? Well, this means the data types that we currently don't have. Which doesn't mean that the data types that we have are sufficient for the CAV. Maybe that's not the case, but we can have an extension, or we can have a new technology if that is found adequate. So this for human CAV interaction, this for environment sensing subsystem, and this for the autonomous motion subsystem. So you see, there is something, but not a lot. So this is the motion actuation subsystem. Therefore, we are looking forward to working with you on this exciting MPI project. This is our logo and our motto: join MPI, share the fun, and build the future. To do that, please go to MPI.community in the How to Join tab, and we are waiting for you to work on this exciting project. Thank you.